Fuel systems look simple only when you look at them from a distance. You see a fuel gas header, a fuel oil loop, a few pumps, heaters, filters, vessels, control valves, knockout drums, storage tanks, and burner lines. But when you are the engineer responsible for keeping a refinery, petrochemical complex, gas plant, utility boiler, fired heater, or gas turbine alive during real operation, you quickly discover the truth. A fuel system is not just a supply system. It is the energy balance, reliability backbone, safety buffer, environmental control layer, startup enabler, emergency survival system, and operating flexibility engine of the entire plant. If the fuel system is weak, everything downstream becomes fragile. The furnace trips, the boiler becomes unstable, the gas turbine flames out, the header pressure swings, liquid enters the fuel gas line, heavy oil cools down and freezes inside piping, atomizers choke, burners lose flame shape, steam condenses inside burner guns, the plant starts flaring energy that should have been recovered. And suddenly what looked like just fuel becomes the reason production, safety, emissions, and availability all begin to collapse together. So today, I want you to look at fuel systems the way a serious design engineer must look at them, not as piping, not as utilities, not as a secondary package, but as a controlled combustion supply architecture that must deliver the right fuel in the right condition at the right pressure, temperature, viscosity, cleanliness, heating value, stability, and availability, continuously. The first principle is availability. A fuel system must supply consumers safely, reliably, and without interruption. That is not a slogan. It drives the entire design philosophy. Critical fuel systems are designed for continuous operation. Equipment that requires regular maintenance must be spared. Pumps, heaters, filters, knockout vessels, heat exchangers, and fired heaters must be arranged so that one item can be taken out without killing the system. For vital rotating equipment, redundancy is not an afterthought. You think in terms of N plus spare capacity and you think about independent drives. 2 electric pumps on the same weak power supply are not real resilience. If the fuel system must survive a major power disturbance, at least one pump may need steam turbine drive or independent electrical supply from a different board. That is the difference between theoretical redundancy and operational redundancy. A second independent fuel system may also be required. A lighter fuel oil may be needed for startup before switching to heavy residue. A backup fuel may be required for emergency operation. A liquid fuel system may need to remain circulating on standby so it is not cold and useless when demanded. A fuel system that cannot respond when needed is not a backup. It is installed decoration. The second principle is fuel balancing. In refinery service, fuel systems often consume low-value byproduct streams generated by the process. These streams are not stable commercial fuels. Their flow, composition, physical properties, and heating value vary. The design objective is to consume these streams efficiently, avoid unnecessary flaring, reduce energy waste, and minimize the need for expensive makeup fuel. This is why gaseous fuel balance is so important. Plant-generated fuel gas must be matched with consumption. If gas production exceeds demand, you flare. If demand exceeds production, you inject makeup gas, LPG, vapor, or natural gas. Both conditions cost money. One wastes energy and increases emissions. The other increases operating cost. Liquid fuel often becomes the balancing medium because it can be stored. Many fired heaters and boilers are designed for dual firing, allowing gas and liquid fuel to be adjusted together. When gas production rises, the fuel gas share can increase. When gas production falls, the liquid fuel share can increase. That is how the plant breathes through operating changes. But balancing must not destroy firing symmetry. You cannot simply change fuel ratios casually and expect uniform heat flux, stable flames, and clean combustion. Good balancing requires controlled discipline. The third principle is combustion quality. A fuel system is not successful because it delivers quantity alone. It must deliver quality. For gaseous fuels, the key variables are pressure, temperature, density, composition, heating value, Wobbe Index, dryness, and cleanliness. Fuel gas composition can vary significantly, especially in refinery systems where multiple streams are combined. The design must minimize both the magnitude and rate of change. Sudden swings in composition disturb air-fuel ratio control, flame stability, heat release, burner performance, and emissions. The fuel gas header must deliver constant pressure. A typical refinery fuel gas system may distribute gas at around 4 bar gauge with sufficient pressure drop allowance for combustion systems and burners. Consumer battery limit pressure should not be allowed to swing excessively. Header buffering, makeup control, vent control, and consumer fuel balancing all exist to protect that stability. Liquid carryover into fuel gas is a serious design failure. Hydrocarbon liquids or water in fuel gas lines can cause burner instability, flame failure, mechanical damage, corrosion, and unsafe combustion. That is why fuel gas systems require central mixing and knockout facilities before distribution, even if the individual consumer also has its own knockout drum. You do not rely only on the last line of defense. You design the main system so liquids should not form in the first place. Condensation risk must be checked under worst operating cases: expansion cooling, water-saturated gas after scrubbing, high butane or heavier hydrocarbon content, low ambient temperature, and pressure reduction across letdown valves. If dew point risk exists, the gas must be heated above dew point, and downstream piping must be heat traced and insulated. The goal is simple: no liquid formation during normal operation. For gas turbines, the requirement becomes even stricter. Gas turbines are intolerant of fuel variation. They require high-pressure gas, often at least 18 bar gauge, and they require dry, clean, superheated gas. Liquid entrainment is unacceptable. Gas must be heated sufficiently above dew point, commonly with a margin such as 20 degrees Celsius above dew point. Wobbe Index control becomes critical because it links heating value and density. A constant Wobbe Index helps maintain heat input for a given combustor pressure drop, but it does not guarantee identical flame character. Hydrogen content, inert content, and gas composition still affect combustion dynamics and flame behavior. This is where inexperienced engineers make mistakes. They think Wobbe Index alone solves combustion. It does not. A gas turbine fuel design must consider composition, contaminants, heating value, pressure, temperature, rate of change, backup fuel switching, and manufacturer combustion limits. For fuel oil systems, the most important combustion variable is viscosity at the burner. Regardless of atomization method, fuel oil entering the burner should be sufficiently fluid for good atomization. A practical design target is that viscosity at the burner should not exceed about 20 centistokes. If viscosity is higher, atomization deteriorates, droplets become larger, combustion becomes incomplete, flame quality suffers, particulates increase, and burner fouling becomes likely. Temperature is therefore not selected casually. It is selected to achieve the required viscosity at the burner after considering line heat loss. For steam atomized burners, there is another critical limit. Fuel oil must not be too cold. If cold fuel causes atomizing steam to condense in the burner barrel or atomizer, burner performance becomes unsafe and unstable. A minimum supplied temperature around 120 degrees Celsius is typically required for steam atomized systems. This is why ambient gas oil is not always a suitable startup fuel for steam atomized burners. It may look convenient, but it can create burner problems. Now let us look at gaseous fuel systems. A refinery fuel gas system collects multiple gas streams, mixes them, buffers pressure swings, removes liquids, and distributes gas to fired heaters and boilers. Its job is to keep gas pressure stable while production and consumption change independently. The system must be designed so low-pressure producers can still enter the collection header. Excessive header pressure can prevent some streams from flowing in, and it can also increase condensation tendency of heavier components. Buffer volume is not just a vessel size calculation. It is an operating stability tool. A buffer or mixing vessel can smooth pressure swings, slow composition changes, and provide liquid knockout. In some cases, high-pressure gas can be routed through a high-pressure buffer vessel, allowing the system to absorb and release gas during normal demand swings without immediate flaring or makeup injection. But a vessel must be maintainable. If the system requires continuous operation, 2 vessels in parallel may be needed, so one can be isolated and inspected, while the other remains in service. If demister mats are used in fouling service, parallel vessels become even more important. The LPG vaporizer is another critical part of many fuel gas systems. Its purpose is not merely to vaporize LPG. Its purpose is to respond fast enough when the fuel gas system suddenly loses a major producer or sees a major increase in demand. The vaporizer must have sufficient capacity and hold-up. It must avoid film boiling. It must use a suitable heating medium. If steam is used, the design must prevent condensate accumulation in the heating coil, because condensate delays response when sudden vaporization duty appears. Backflow protection is essential. A tube rupture in a steam-heated LPG vaporizer can send hydrocarbons into the steam system unless non-return protection, pressure detection, and isolation logic are provided. Butane-rich LPG introduces a special hazard. Butane and heavier components may condense in the fuel gas system after vaporization and pressure reduction. The designer must calculate worst-case dew point and ensure the gas is heated and kept above that dew point. Flare gas recovery is another important concept. Flaring is not only an environmental issue, it is also energy loss. Recovering suitable flare gas and compressing it into the fuel gas system can reduce flaring and recover useful heat value. But recovered flare gas may contain inerts, so its effect on final fuel gas composition must be checked. Low-pressure gas is a separate case. If it is liquid-free and has heating value comparable to fuel gas, it may be worth using in a dedicated low-pressure system for nearby furnaces. But it must still be controllable and safeguardable. If it is too low in pressure, too erratic, too inert, too corrosive, or too contaminated, it is not fuel gas. It is waste gas, and it needs a different disposal philosophy. Now let us move to liquid fuel systems. Refinery fuel oil systems are often the backbone of plant survivability. They may support startup, normal operation, emergency utility firing, and balancing of fuel gas demand. But not all liquid fuels are equal. The design is governed mainly by viscosity, stability, pour point, contaminants, storage behavior, heating requirement, and combustion suitability. Long residue fuel systems, short residue fuel systems, and asphalt burning systems differ mainly by fuel heaviness and operating temperature. Long residue may require distribution temperatures around 100 to 160 degrees Celsius to reach the required burner viscosity. Short residue may require roughly 160 to 220 degrees Celsius. Asphalt systems may operate even higher, with distribution temperatures reaching the range where thermal cracking and coking become real threats. Heavy residue fuel is not just hot oil. It is a difficult, unstable, contaminant-rich combustion material. It can contain sulfur, nitrogen, metals, ash, coke particles, and asphaltenes. It can cause emissions issues, fouling, corrosion, particulates, high NOx, and incomplete burnout. That means the fuel system cannot be designed in isolation. The fired equipment must be suitable for the fuel. The flue gas side must tolerate fouling. Emission limits must be met. Convection bank cleaning and corrosion control must be considered. Blending is another danger area. Heavy residues may need low viscosity diluent to meet handling and atomization requirements. But incompatible blending can cause asphaltene flocculation, fouling, sludge, and filter blockage. Straight-run residues and thermally cracked residues may not mix well. Laboratory compatibility testing is essential where uncertainty exists. The storage tank is not a mixer. Good mixing must be achieved using proper blending methods, and static mixers may be unsuitable for cracked fuels because they can block. Fuel oil circulation loops must be designed for pressure, temperature, filtration, heat loss, and flow stability. Fuel is taken from storage, pumped, heated, filtered, distributed to consumers, and returned through a controlled loop. Return flow is not waste. It maintains temperature, circulation, and readiness. Fuel oil pumps must be spared. A common arrangement is 3 pumps, each size, so 2 running pumps can support normal operation while the third remains standby. The standby pump must start automatically on falling pressure quickly enough to prevent consumer trips. Heaters must also be spared. If one heater is offline for cleaning, required duty must still be maintained. Heater outlet temperature must account for line heat loss, but the oil film temperature must not exceed the temperature where fuel degradation, cracking, flashing, or coke formation occurs. A typical upper film temperature design concern is around 330 degrees Celsius for heavy residues. Filters are not optional. Suction strainers protect pumps. Hot pressure filters protect burners and downstream equipment. Filters must be 100% spared, switchable online, equipped with differential pressure monitoring, and designed for safe flushing and cleaning. Heat tracing and insulation are equally critical. In heavy fuel service, a cold line can become a blocked line. Heat tracing must keep stagnant fuel pumpable, but overheating stagnant fuel can cause coking or vaporization. So tracing design must balance fluidity against degradation risk. Thermal expansion relief is required for isolated sections. Flushing provisions are essential, especially for short residue and asphalt systems. Before shutdown or maintenance, heavy fuel must be displaced with compatible lighter fuel or flushing oil. But the flushing medium must not flash when introduced into a hot system. Backflow from heavy fuel into flushing or steam systems must be physically prevented. Now consider the asphalt burning system. This is one of the most demanding liquid fuel systems in refinery service. Asphalt systems handle very heavy residues and residues that may generate vapor during storage due to after cracking. The fuel must be characterized before design, viscosity-temperature relationship, cracking tendency, storage behavior, contaminants, and required burner viscosity temperature. Asphalt circulation must be strong enough to limit temperature loss throughout the loop, often targeting no more than about 20 degrees Celsius loss between heater outlet and loop return. The return flow may need to be as high as the consumption rate, with adequate velocity to prevent stagnation. Dead legs are dangerous. Subloops must be arranged to keep circulation near consumers. Offtake lines should be short and taken from the top of the line. Isolation and flushing must be provided so a subloop can be removed from service without sacrificing the whole system. Asphalt storage is normally minimized. Hot rundown from the process unit is preferred where possible. If storage is required, blanketing, venting, heating, mixing, and temperature limits become major design topics. Steam heating is generally avoided where water ingress into asphalt is unacceptable. Heat transfer fluid or electrical heating with surface temperature protection may be needed. The asphalt surge drum is not just a volume. It is the operating stabilizer between supply and circulation. It must provide holdup for supply interruptions, allow time for corrective action, and maintain positive pressure. Vapors from after cracking must be routed safely for incineration or controlled disposal. Instrumentation in asphalt service must be robust and redundant because loss of correct heating or circulation can destroy operability. Overheating creates coke, blocked filters, fouled heater coils, and burner blockage. Loss of circulation creates cooled, blocked, immovable asphalt in the distribution system. Control valves must be spared where critical. Pressure measurements may need multiple transmitters. Instrument tappings must be short, heat traced, and insulated. Control valves must be heat traced. Return control valves may need mechanical minimum stops to preserve circulation even during abnormal control conditions. That is engineering discipline, not decoration. Discipline. Low boiling fuel systems are different again. Light tops, naphtha, gasoline, and similar liquids may be used intermittently for disposal of off-spec products. They require completely separate systems from fuel oil. They should not be heated. Leaks are serious fire hazards. Non-welded connections must be minimized, especially near furnaces. These systems normally use pressure atomization, simple bare headers, storage sized for batch disposal, and 100% pump capacity redundancy. Gas oil has a narrower role than many engineers assume. It is less preferred as a furnace startup fuel in modern steam atomized oil systems because ambient gas oil can cause atomizing steam condensation and poor burner behavior. Its more practical role may be flushing medium or diluent for residual fuel systems, although it should not be used in very hot systems where vaporization can occur. Finally, oil and water emulsions offer another route for very heavy residues. By suspending fine oil droplets in water with surfactant, viscosity can be reduced. But this creates its own design consequences. Higher fuel flow because water may be a large fraction, higher water content in flue gas, possible stack plume issues, and the same underlying contaminant problems from heavy residues. Even if the emulsion viscosity is acceptable without heating, steam atomized burners still require sufficient fuel temperature to avoid condensation of atomizing steam. So the lesson is clear. Fuel system design is not about connecting available fuel to available burners. It is about controlling volatility, viscosity, pressure, heating value, Wobbe Index, dew point contaminants, storage, circulation, response time, sparing, flushing, emissions, and emergency continuity. A weak fuel system shows up during transitions: startup, shutdown, producer trip, consumer trip, power failure, fuel switchover, sudden demand rise, low ambient temperature, fouling, blocked filters, stuck control valves, failed heaters, failed tracing, and unstable combustion. That is when design quality becomes visible. A good fuel system gives the plant options. It allows gas and oil balancing. It avoids flaring. It protects burners. It keeps utilities alive. It enables safe startup. It manages heavy residues. It prevents liquid carryover. It keeps fuel oil pumpable. It supports gas turbines without violating combustion limits. It turns difficult byproduct streams into controlled energy instead of uncontrolled risk. And that is the engineering mindset I want you to carry forward. Do not design fuel systems as utility side notes. Design them as mission-critical energy management systems. Because in real plants, fuel is not just what burns. Fuel is what keeps the entire facility alive when everything else is changing.